In this video, I will present the results of a reproduction study of a paper, Strategic Classification Made Practical, by Sagi Levanon and Nir Rosenfeld. The reproduction was performed by me, Maximilian Kulicki, Gili Colquhoun, Jan Atmer, and Alex Labro from University of Amsterdam. So, what exactly is strategic classification? It's a setting in which a prediction model tries to classify users, and the users know about this process and change their behavior to modify the outcome of the classification. This can happen in systems such as insurance decisions about loans, or detecting spam or fraudulent behavior. If we have a naive classifier, a user who is close to the boundary can slightly change their behavior to end up on the other side of the boundary, which is a more favorable outcome for them, but it's an incorrect classification. A strategically aware classifier will modify the boundary to prevent this behavior. This happens under the assumption that the cost of changing the behavior is known. This way, the boundary can be set up in such a way that the cost of modifying the behavior becomes larger than the reward of a more favorable outcome. This idea was already presented in previous papers. What this paper contributed was a new framework that can support complex nonlinear models, can handle adjustable and unknown cost functions, can regularize for different metrics of social good, and it was evaluated on 4 real-world datasets. We were able to run their code and reproduce the results successfully. In addition to that, we ran a few new experiments to test the robustness of the presented framework. We identified an important limitation of the system, which assumes uniform behavior of all users, and that all users will try to optimally game the system. For example, in a spam detection setting, a spammer will try to optimize their behavior to fool the system, but also regular users will try to game the system to be classified as non-spam, which is likely not the case and might lead to regular users being falsely labeled as spammers. In our experiment, we randomly assigned each user as either gaming or non-gaming. A gaming user will modify their behavior optimally according to the cost function, and a non-gaming user will not modify the behavior at all. 3 of the datasets in the paper were classified using a linear model, and 1 of them was classified using a recurrent neural network. We observed a clear linear relationship between the accuracy of the linear models and the number of gaming users. With more gaming users, the strategic model was better, and with more non-gaming users, the non-strategic model was better. This confirmed our hypothesis. We also saw that the strategic model was making false negative errors when classifying non-gaming users, and that the non-strategic model was making false positive errors by classifying gaming users as positive. However, the results of a recurrent neural network model were significantly different. Somehow, the strategic model has learned a representation that could deal equally well with gaming and non-gaming users alike. The non-strategic model, just as previously, was misclassifying gaming users as false positives. However, the strategically aware classifier obtained a high accuracy of gaming users with no loss in accuracy with respect to non-gaming users. To summarize our contribution, we extended the existing framework by considering varying behavior of users. We identified a clear limitation of strategically aware linear classifiers, and we found a promising new avenue for research with regard to non-linear strategically aware classifiers, which can possibly deal with both gaming and non-gaming users in the same system.